Let's talk about the backshift operator and the backshift or operator notation. This notation is going to allow us to access some very interesting and very useful theoretical results about our time series models. But let's just jump right in and define what the backshift operator is. BK operated on xt is BK xt equals simply xt minus k. It allows us to represent the lag information in the form of an exponent, which is again going to be very, very useful. But let's look at a couple of examples on how to actually put time series models into this backshift notation. Let's look at an AR1, and specifically, let's say that this is xt equals 0.9 xt minus 1 plus at. Awesome. So the first thing I'm going to do here is put the x's on one side, on the left side, and the ATs, the white noise terms, on the right side. So that form is also going to become very useful to us. So that'll be xt minus 0.9 xt minus 1 equals AT. And then I'll put that in backshift notation. That would be 1 minus 0.9 B xt equals AT. And here's where I like to check it. It's xt times 1 is xt, and xt times negative 0.9 b. b operates on the xt to give us xt minus 1, and so there's negative 0.9 xt minus 1. Great, it all checks out. So now let's look at an AR2 for some more practice, putting this into backshift or operator notation. So let's say that I've got xt equals 0.2 xt minus 1 plus 0.63 xt minus 2 plus our white noise term, AT. So putting that into backshift notation, we are going to have xt, actually let's get all the x's on one side first, minus 0.9 xt minus 1, or 0.2 xt minus 1, minus 0.63 xt minus 2 equals AT. Okay, we've got all the x's on one side, all the white noise terms on the other. Now we're in a position to put it into backshift notation. So it's 1 minus 0.2 b minus 0.63 b squared, all of that times xt equals AT. And so there we have it. That's in backshift notation. Awesome. Let's look at one more example here. We'll talk this time about an AR4, just to show that in a backshift notation form. So let's say we have the model xt equals 1.2 xt minus 1 minus 0.29 xt minus 2 minus 0.702 xt minus 3 plus 0.648 plus 0.648 xt minus 4 plus AT. Great. Okay, same thing, just AR4 now. So we're going to put all the x's, all the information about the x's on the left side and all the white noise terms on the right side. So I'm going to have here xt minus 1.2 xt minus 1 plus 0.29 xt minus 2 plus 0.702 xt minus 3 minus 0.648 xt minus 4. All of that equals AT. Now we've separated the x's and the ATs. Now let's put it in backshift notation. So now that's 1 minus 1.2 b plus 0.29 b squared plus 0.702 b cubed minus 0.648 b to the fourth, whole thing times xt equals AT. Let's check. Xt times 1 is xt. Xt times negative 1.2. B times xt is xt minus 1. There's the minus 1.2 xt minus 1. And then xt times 0.29 b squared. That's 0.29 xt minus 2. There's 0.702 times b cubed times xt. That's 0.702 xt minus 3. And negative 0.648 b to the fourth xt, x to the fourth right there, minus 0.648 xt minus 4 equals AT. So great, we've got it into backshift notation, just a little kind of planting seeds for the future. What we've done here is to write this lagged information, this information about the lags, into what will become a polynomial form, but recalling that this b right now is actually an operator. It's not a variable yet, but we'll see that in the future. This is Backshift operator notation. Great job. See you in the next one.